Welcome back to the third and final part of this workshop. In this part, our main focus would be to extend our knowledge of 2D CNN to a 3D CNN and explore transfer learning. 3D CNNs, as the name suggests, work in 3 dimensions. To train a 3D CNN, we require a set of images rather than a single image. Examples of these include video classification, where video is a collection of many frames, and frames here are nothing but images. Medical imaging is also one of the most popular areas for 3D CNNs, where three-dimensional mappings of tissues, organs, etc. are used to diagnose patients. Because of an additional dimension a 3D CNN introduces, the kernel has an additional dimension of depth in a 3D CNN. In addition to the horizontal and vertical traversal, the kernel also traverses the depth of the input data, as you can see in the image below. We have seen how a 3D CNN requires an extra kernel dimension, and also the images now need to be passed as a collection rather than a single image. Now these are the two features that differentiate a 3D CNN from a 2D CNN, and to implement these from scratch may take us days to complete. However, Keras comes to our rescue again. Keras has a layers API for the 3D CNN which enables us to design our model in a way similar to 2D CNNs. If you recall, in part 2, we had used the layers API of Keras to design our 2D CNN architecture. The same layers API also supports the 3D CNN model. For the convolutional layer, we now use Con 3D layer instead of Con 2D layer. And now the kernel size is a 3-dimensional vector rather than a 2-dimensional vector. Similarly, for the pooling layer, we now use max pooling 3D instead of max pooling 2D. Once again, the dimension of the matrix increases by 1 and hence we supply a 3-dimensional vector for the pool size. In summary, a 3D CNN is just an extension of a 2D CNN, and the primary difference is that a 3D CNN has one more dimension than a 2D CNN. Now let's dig deeper into an interesting approach of building machine learning models: transfer learning. Transfer learning is a machine learning method where a pre-developed model is reused as a starting point for another task. It is a popular approach where a pre-trained, state-of-the-art model is used to achieve a task rather than training a model from scratch. The advantages of transfer learning are as follows. Model development time. Most of the model is pre-trained and hence this reduces the development time of the model. High performance architecture. The model has already been tested before, and it is a state-of-the-art model, which means that the performance is usually much higher than a model which is trained from scratch. Larger training dataset. Most of the base models which we use in transfer learning are often trained on millions of images, and these are very large training datasets. The ImageNet project. Even though most of you are excited to see transfer learning in action, it is important that we spend some more time to understand the origin of some of the state-of-the-art models that form the base of transfer learning. Most of the computer vision models used for transfer learning share a common history: the ImageNet project. The ImageNet project is a large visual database designed for use in visual object recognition software research. Since 2010, the ImageNet project runs an annual software contest, the ImageNet Large Scale Visual Recognition Challenge, the ILS-VRC. The model that wins this competition is often regarded as a state-of-the-art architecture in computer vision. Our dear friend Keras helps us use these excellent pre-trained models for our own personal use with just a few lines of Python code. Let us now explore one of the state-of-the-art architectures called the VGG16. The VGG16 was proposed by Karen Simonian and Andrew Zizerman of the Visual Geometry Group Lab of the Oxford University in 2014. In the paper called Very Deep Convolutional Networks for Large-Scale Image Recognition. The ImageNet dataset contains images of fixed size of 224 times 224 and have RGB channels. So the VGG16 has an input tensor of 224 times 224 times 3. As you can see in the picture below, the VGG16 has 13 convolutional layers marked in blue, 5 max pooling layers marked in red, and 3 dense layers marked in green, which classify up to 1,000 categories. If you look at the last dense layer, which has a dimension of 1 cross 1 cross 1,000, it signifies the fact that the last dense layer has 1,000 neurons, which, if you remember, in part 2 as discussed, corresponds to 1,000 categories. Now if you count the number of blue layers and green layers, in other words, if you sum total the number of convolutional layers and the fully connected layers, it will add up to 16. And this is the reason behind the 16 in VGG16. Surprise! We have a bonus for you. What if we implemented transfer learning in the car logo classifier we just made? This is exactly what we are going to do next. So this is your chance to pause the video and grab a cup of coffee as we dive deep into the implementation of transfer learning using Python. So welcome to the last part of this particular workshop. In this part, our aim is to implement the VGG16 model and use it to solve the car logo classifier problem, which we had previously solved using the 2D CNN architecture we had created ourselves. So the first thing we need to do is we need to import all the libraries to start our project. Now these include, of course, some functionality from Keras. So from keras.layers, we need input, lambda, dense and flatten, and from keras.model, we need to import model. Secondly, we will also need to import the VGG16 model. This again is there in Keras, and Keras helps us to download the VGG16 model. After we are done with that, we need some pre-processing and data augmentation libraries. So from keras.preprocessing, we'll import image, and from keras.preprocessing.image, we'll import the image data generator, which we'll use for data augmentation. And finally, for plotting and some numerical computation, we'll need numpy and matplotlib.pyplot. Now this particular environment that you see right now is called Atom. Atom is a text editor and is different from the environment we used before, which was Jupyter Notebooks. To run a code or a piece of code in this particular interface, all you need to do is select it and press Shift and Enter. It is also important to note that Atom in this case has been attached with another add-on called Hydrogen, which enables this feature. So this is just to give you an idea how different environments can be used to code, and it doesn't really matter which environment you are using, and that is what I mean to convey over here is that all these codes are independent of the environment you're using. You can use Atom, you can use Jupyter Notebooks, or any other environment of your choice. Alright, let's get back now to the image size. Now one important thing I'll need to mention over here is that the VGG16 model was originally made to take an input dimension of 224 times 224 pixels of images which were made in the RGB color scheme, which means that your input data has to be of the dimension 224 times 224 times 3. Here the 3 represents the 3 channels for RGB. So that is what we have done over here. We have declared a variable called image size and we have given it a list of 224, 224. Secondly, we need to specify the addresses where our training and the test data set are kept. Now it is very important that you understand that these addresses are with respect to my local machine, and you need to change it to the address where the dataset has been kept on your machine. So this has to be changed if you're trying to run this code on your computer. Next, what we need to do is we need to tweak the VGG16 model a little bit. And why do we need to do so? Well, the need arises because of the fact that the VGG16 model was originally developed to classify 1,000 different categories. Now, as you remember, as we talked in the lecture before, that the last dense layer has a certain number of neurons, and these number of neurons correspond to the number of distinct categories that you need to classify. Now, because the VGG16 model was initially made for 1,000 categories, the last layer of the VGG16 has 1,000 neurons. Now, if we do not change this, then it's going to be a disaster for us because we just have 10 distinct categories. So what we do is we say include top equals to false, which means that we do not want to include the last dense layer of VGG16. Secondly, we specify that the weights should be equal to ImageNet. Now, if you recall from a discussion in the lecture, ImageNet is the contest where VGG16 was originally introduced. And when we say weights equals to ImageNet, we basically mean that we want to use the same weights that were used in the ImageNet contest. And last but not the least, the input shape has to be specified. And as I said, the input shape is 224 times 224 times 3. So once we're done with that, the next thing that we need to do is we need to tell the machine that we do not want to change the weights that were already used in ImageNet. And to do so, what we do is we develop a for loop and we set the layer and we set the trainable parameter of each layer to false. So for layers in vgg.layers, layer.trainable equals to false. Now what does this mean? Well, when we actually trained our custom 2D CNN architecture, all the variables that we introduced were trainable, which means that the computer has to find out the optimum values for all these variables. But in this case, we are saying that we do not really want to change the values that were originally used in the ImageNet project, and we want to keep the same values. In other words, we do not want to train those variables, and hence we set the trainable parameter to false. So you might ask me, if we are setting the trainable parameter to false, what exactly are we training? Isn't the model already, learned? Does the model need to learn again? Well, if you realize that we actually have taken out the last layer of VGG16, which means that we'll also need to add another layer to the VGG16 model, which has 10 neurons. Now, these are the 10 neurons that will actually be trained and will help us in the classification. So you're right when you say that a lot of the model has already been trained, but not the entire model is not actually trained. We also have the last layer which requires some training. So now let's see what this particular piece of code does. It says folder equal to glob and which has an address over here. Now what this particular line of code does is that it goes to this particular address and it finds the number of directories that are present in that address. Now it makes a list of all those directories and saves it in this variable called folders. For example, let me just run this line of code and you'll understand what I mean. So the number of categories are the first address to the first directory, the address to the second directory, the address to the third directory, and so on. Now, as I said that we removed the last layer of VGG16 because we did not want 1,000 neurons, but now we need to add another layer to the end of VGG16 so that it has 10 neurons and we can classify all our categories perfectly. So to do that, we use these two lines of code. So what these two lines of code basically mean is that flatten the output that the VGG16 has and add another layer to the end of VGG16, which will have the total number of neurons equal to the length of folders. Now the length of folder is the number of directories that we have. And as you recall, the directories are basically our categories. So length of folders is nothing but the number of categories. So once we're done with that, we create the model using this particular line of code. Model equals to model, inputs equals to vgg.input, and outputs equal to protection. And then if we print the model summary, so let me just run these lines of code, and you'll see that if we print the model summary, we'll have a large number of non-trainable parameters. Now, why do we have such a large number of non-trainable parameters? It's basically because of the fact that we use this for loop to set the trainable parameter of all layers in VGG16 except the last layer to false. So if you look at the numbers over here, you see this number 250890, and the trainable parameter is also equal to the same number. This reevaluates the fact that the number of trainable parameters are only present in the last dense layer of our VGG16 model. So once we are done with looking at the summary, we can compile our model with a loss function, an optimizer, and our metrics. Then we start with data augmentation. Over here, my main aim is not to introduce data augmentation, as we have already done that in the 2D CNN architecture, in the custom 2D CNN architecture we went through. So over here, I've just added 3 types of data augmentation. One of them is, of course, rescale, the other is zoom range, and horizontal flip. And all of these have been discussed in the lecture. Similarly, for the test dataset, I also introduced a rescaling factor as a data augmentation technique. And then we had set up the data pipeline using the flow from directory function of Keras. And let me just run all these lines of code so that we have a data pipeline ready. Let's say it found 10,000 images belonging to 10 classes, and it found 1,500 images belonging to 10 classes for the test dataset. And this is exactly what we had before. So now we just need to train this model, and to train this model, we have to execute this particular line of code. Now, this is going to take a lot of time, so we are not just going to wait till it completes training, but rather we'll just start its training, and you'll see that the number of epochs declared over here is 2. So to train for 2 epochs, the validation data set is basically the test set, the variable right over here, and the steps per epoch is the length of the training set, validation step is the length of the test set. Now, as you can see over here, it has started training on the first epoch, and it's going to take a lot of time, so we're not going to wait for it, and we'll just move forward. So the last thing, once your model has been trained, what do we do next? If you recall, it's the same procedure as a 2D CNN. We plot the loss and the accuracy to see how well our model has performed. And if you're not happy with the model performance, you can go forward, change the number of epochs, or maybe introduce new kinds of data augmentation techniques and train it again. And once you're satisfied with your model performance, all you need to do is save your model, and to do that you can use model.save command over here. And to load the model, follow the same steps that we did in the 2D CNN project. So to sum it all up, in this case what we did is we didn't really make our own architecture, rather we used a custom architecture which was already present in Keras called the VGG16. Now you may tell me that the VGG16 is one such architecture. Can I use the others? Well, of course, yes, you can use the others. There are others like VGG19, there are AlexNet, and all these different kinds of architectures which have been tested, and they usually work pretty well in all the scenarios. And so you can try and play around with all these architectures until and unless you come with an architecture that has an accuracy which you desire. So that is the main aim of transfer learning. You don't really have to spend a lot of time training the parameters, because as you can see in the CNN architecture, most of them have already been trained, and so it's just 250,000, approximately 250,000 parameters that you need to train. Suppose that all these parameters are not trained, then just add these two numbers and see how many parameters you would actually need to train. And more the number of parameters you need to train, the more time it takes. And so transfer learning is a really good technique to help you lower down the development time and build models which have high or reasonable amount of accuracy. So I hope you enjoyed this video and learned about transfer learning and how to implement it in Python.